Hi there, my name is Christopher Wurst and welcome to the final video of part of the homework 1 for transport. This is going over part 4 that says a cylindrical cup of radius r and height h is filled with water to a level of h naught. Derive an expression for the maximum angular frequency omega. The cup can be rotated to without spilling the contents. Now, as you know, I'm going to start with drawing a picture on the whiteboard behind me, and then move on to deriving the equations. So, let's get started with drawing a picture. So in scenario 1, a cylinder is filled with some liquid, we'll call it water, to some height of h naught. This cylinder or this cup has a maximum height of capital H. And a radius of capital R. It's also asking what the maximum angular frequency is, and we can spin it without the cup overflowing. So I'm going to draw a second scenario. The water or the liquid line is somewhere down here. The initial liquid line is here. And then at this center point, the liquid is coming down, then back up. So with this over here, this liquid transforms into this liquid. Okay. We're also going to label this difference in height from h naught to where this lowest point is as d. And that should be it for the drawings. Now I'm going to start out by writing out some initial equations that will be used later. So we've got our usual, basic equation of fluid statics, which is change in pressure over, instead of dz, it's now going to be dr, because we're not curious about a change in height. We're actually looking at a change in radius, i.e. as it's spinning. dr is equal to, same thing, density of the fluid, and it was g in the height equation because it was being affected by gravity. Now it's not being affected by gravity, where it's more so being affected by the angular acceleration. So we're going to call it a theta. We also know that angular acceleration, is equal to the angular frequency squared multiplied by r. So omega squared r. And there's our omega, so it will be there in the future. And then we know that pressure is equal to pressure is equal to rho gh. So the density of the liquid multiplied by the force of the acceleration due to gravity multiplied by the height. So rho gh. Okay. So we're going to start with this. So with the basic equation of fluid statics. dP over dr is equal to rho acceleration in the angular acceleration, which then goes to, as we substitute in angular acceleration, dp over dr is equal to density of the fluid times angular frequency squared times the radius. We now have radius, so we can separate it. So we have dp is equal to, change of pressure is equal to rho, the density, multiplied by angular frequency, multiplied by r dr. Radius times change in radius. Now, we can now integrate, so I'll put the integration here and here. These two don't go in the integration because they are constant. So we are starting at radius 1 here, which is big R, or we're going to call it radius 1. And then it's going to go to R. Actually, sorry, specifically radius 1 here. And then it's going to go to some R, which will end up being this capital R of the radius. So R1 to R. I'm also going to mark these as R primes, just so they're dummy variables. And then pressure 1 here, and then pressure up here. So pressure 1 to some pressure. Again, dummy variable. So this goes to, dP goes to pressure from initial pressure to some arbitrary pressure is equal to density times angular frequency times r squared over 2, r squared over 2 from R1 to R. Goes to pressure, it would be pressure minus initial pressure, so I'm just going to add that over. So pressure is equal to P1 plus density, angular frequency. This would be R squared over 2, oops, over 2 minus R1 squared over 2. And in this initial, scenario, R1 at this dot is equal to 0, so this cancels. And then the pressure at P1 is also equal to 0 because there's nothing pushing out. There's no force. It's at the, or there's no angular force due to it. And the only thing actually up there is air. So P1 is equal to 0, which then means pressure is equal to density, angular frequency, radius squared over 2. Now I'm going to copy this, we'll call it over here, and I'm going to erase all of this after. So pressure is equal to density, angular frequency, or radius squared over 2. And let's erase and get more room. Now I'm going to take this and plug in rho GH. So pressure is equal to density, angular frequency, radius squared over 2 goes to density, acceleration due to gravity times height is equal to density, angular frequency, radius squared over 2. These two densities cancel. They go to h, and we move this gravity over to a height is equal to angular frequency squared times radius squared all over 2g. Now, in this specific setting, here, we're going to say that radius is equal to big R. Big capital R squared, it is equal to this R. So, I'm also going to copy that over here, because this will be important later. Height is equal to, and specifically, this is the height of this h. It's equal to angular frequency times the radius of this cup squared divided by 2 times the acceleration due to gravity. Okay, we have that. I can erase all of this. And now the last thing that we want to find before we plug everything together to get to single out this angular frequency is we want to find d. So we know that the area or the fluid, the volume of fluid here in this lined section is the same as this fluid, the volume of fluid here. So we'll call this V1 is equal to V2, goes to volume 1. We can calculate what volume 1 is equal to, however, it's difficult to calculate the volume of this because it's an unusual shape. So this will be the area or the integral of the, call it, the integral of the area, d area, it'll be the integral of, which will end up being a, we'll call it dv, integral of dv. Now, this v1 is simple, that is just pi r squared with r being the big R, pi r squared times d. Pi capital R squared times that d, where the d is the difference between h naught and this specific, the height of this, of the bottom of this depression, is equal to the integral of, now we're going to use the area of a cylinder for this, so it will be 2 pi r h dh. Nope, I'm sorry, this is dr. Yes, because h will no longer, will be changing to substitute into this. By the way, this is also, this is a specific case. The general form is omega squared small r over 2g. Yeah. Just for uniform variables. So goes to pi radius squared d is equal to the integral of, I'm actually going to, no, we'll keep it in there. Pi integral 2r h is omega squared r squared, so angular velocity squared multiplied by the radius squared divided by 2g, 2 times acceleration due to gravity times dr. These cancel, these pi's cancel, this gravity, this acceleration due to gravity, this omega squared can be moved out because they're constant. So it goes to r squared d is equal to angular frequency omega squared over acceleration due to gravity g. The integral of these two r's combined, so r radius cubed dr, and this will be specifically from 0 to r. 0 to r. Now, this goes to, sorry, not, yeah, capital R. This goes to r squared d is equal to omega squared over g. This is r to the fourth over 4, r to the fourth over 4 from 0 to r, capital R, which then goes to, which will then become just capital R to the fourth over 4 because it will be minus 0 minus r equals 0, which is 0. I am then going to move this r squared over, so this and this will cancel out. So this r is gone, this 4 is gone, and makes it squared. So, long story short, goes to d is equal to angular frequency squared times r squared over 4 times the acceleration due to gravity. I'll write that over here and then erase all of that, and we can get to the final bit, which is just putting everything together. So d is equal to omega squared r squared over 4g. Okay, last thing. And just to encompass the scenario to make things to get everything able to be plugged in, we know that the height h is equal to h naught minus d, i.e. this bit. This is h naught minus d plus h. So h naught minus d plus h. And you know what? We have equations for these two. So let's plug them in. It goes to full height of the cup is equal to starting position of the starting height of the liquid minus d, which is angular frequency squared, radius of the cup squared over 4 times the acceleration due to gravity, plus h, which is angular frequency squared, radius of the cup squared over 2 times the acceleration due to gravity. This will be gone, and this will become 4g, because in order to add these together, you multiply this by 2, so you get 2 times omega, 2 times omega squared, which is the angular frequency squared, multiplied by the radius of the cup squared, divided by 4g, 4 times the gravitational constant, or acceleration due to gravity, and then those go together. The 2 is gone, so you're left with just this but positive. I'll draw it out. I'll write it out. So height of the cup is equal to starting position of the liquid plus angular frequency squared, or radius of the cup squared over 2 times acceleration due to gravity. We want this alone so we can have it. So I'm going to bring this over, so h minus h naught divided by r squared multiplied by 2g. So angular frequency squared is equal to 2 times acceleration due to gravity, height of the cup minus starting position of the liquid divided by radius of the cup squared, goes to, of course, square root everything. Angular frequency is equal to 2 times the gravitational constant, the acceleration due to gravity, multiplied by some height of the cup minus the starting height of the liquid divided by, this is r, because this square root will cancel with the r squared, and with that, we're finished. Thank you very much for watching. Hope you have a fun time watching this this homework. Have a wonderful day.